All right, today we are tackling a huge one, an idea in physics that's as famous as it is misunderstood, Heisenberg's uncertainty principle. Now, most of us think we know the gist, but it turns out there's a much, much deeper story. So let's get right into it. This is it. This is the version we all learn in school, right? It's the pop culture shorthand for all things quantum weirdness. The more you know exactly where a particle is, the less you can possibly know about where it's going. It sounds like a fundamental law from the universe saying, nope, you can't do that. But here's the twist. What if that statement, that absolute hard line in the sand, is actually missing the whole point? What if impossible isn't really the right word to describe what's going on at the quantum level? So the source material that we're digging into today actually calls this common viewpoint a limited perspective. And the argument is if we only see uncertainty as a barrier, as a limitation, we're totally missing a more profound and honestly more useful truth about how the universe actually works. This whole traditional limited view, it's really built on a foundation of three core no-go statements. You can think of them as the classic, old-school rules of the game, the things that quantum mechanics supposedly forbids you from ever doing. Okay, so let's quickly break down these rules, because they're the pillars holding up this entire idea of uncertainty as just a restriction. Okay, so rule one is the preparation rule. You just can't create a particle that has a perfectly pinpointed position and a perfectly pinpointed momentum. Can't be done. Rule two, the measurement rule. You can't build an experiment to perfectly measure both of those things at the exact same time. And rule three, the disturbance rule. The very act of measuring one thing, like position, is going to inevitably mess up the other thing, its momentum. So you put all those together, and yeah, the message seems pretty clear. It looks like a giant wall, a cosmic dead end. It tells us all the things we can't do. But, and this is what our source material points out so brilliantly, that's only one side of the coin. Now, this is where the story gets really, really interesting. It's time to flip the script and look at the positive role of uncertainty. This isn't about what's forbidden anymore. This is about what's actually made possible. And this right here really nails the shift in thinking. The old view saw position and momentum as strictly mutually exclusive. You get one or you get the other. Pick one. But the deeper, more accurate view sees it as a quantitative trade-off. It's not an either-or anymore, it's a negotiation. The source paper just puts it beautifully. It says the principle plays a positive role. It's not a barrier, it's a bridge. It's the rule book that actually allows these two seemingly incompatible ideas to find some common ground. So, what do we mean by a trade-off? Well, think about taking a picture in a dark room. You need a fast shutter speed to get a sharp, unblurry image, right? But you also need to leave the shutter open long enough to let in enough light. You can't have a perfectly sharp image and a perfectly bright one at the same time. You have to trade a little bit of sharpness for a little bit of brightness. The uncertainty principle is just like that, but for the fundamental fabric of reality. And here's the crucial takeaway. The principle isn't just a big cosmic no. It's actually a yes if. Yes, you can know something about both the position and the momentum, if you're willing to live with a little bit of fuzziness in both. It actually provides the rules for how to make those approximate measurements possible in the first place. Now, this whole trade-off idea, this new perspective, it doesn't just show up in one way. It actually has three distinct but related faces. Remember those three no-go rules from before? Well, each one has a positive trade-off counterpart. For state preparation, it's a trade-off between how spread out the possible positions are versus how spread out the possible momentums are. For measurement, it's a trade-off between the unavoidable inaccuracies of your position measuring tool and your momentum measuring tool when you try to use them together. And for disturbance, it's a trade-off. The more precisely you measure position, the more you're going to mess up momentum. But hey, if you accept a slightly less precise position measurement, you can limit how much you disturb it. It's a balance. So this is a beautiful picture. Theoretically, it makes a lot of sense. But how do we know it's really true? I mean, how do you take an idea like this from a blackboard and test it in a real lab? And you know, for the longest time, that was a huge problem. As the historian Max Jammer pointed out, for a principle that is so central to all of physics, it was shockingly hard to test directly. It was kind of this accepted truth that hadn't been rigorously proven over and over. But that has completely changed. I mean, modern physics has totally risen to the challenge. Physicists have come up with these brilliant theoretical models, like the Arthurs-Kelly model, that actually show how to design these joint approximate measurements. And even better, experiments today can actually build these setups and test the precise nature of these trade-offs, showing rigorously that the theory holds up. Okay, so let's bring this all home. We've gone from a simple, hard no to a much more subtle and powerful yes if. The uncertainty principle isn't a bug in the system, it's a core feature. It's a principle of possibility. And here it is. This is the ultimate takeaway, pulled right from the source paper. The uncertainty relations are the necessary and sufficient condition for being able to know approximately both position and momentum. It's not the thing that stops us, it's the very thing that makes knowing both possible at all. Think about that. Without it, you could only ever know one or the other, perfectly, and be totally blind to the rest. So the next time you hear about Heisenberg's uncertainty principle, don't think of it as a barrier. It's not a wall. It's the rulebook. It's the fundamental operating system that allows two seemingly contradictory ideas, where something is and where it's going, to meaningfully coexist in this strange, beautiful quantum world of ours. And that just leaves us with a final thought to chew on. What other fundamental limits in science do we see as walls, when they might actually be guidebooks, showing us the subtle and elegant rules for how things are actually possible? Thanks for joining us for The Explainer.